Hello fans of structural dynamics. Here is a tutorial and I'm starting with the summary. The summary is important because I want you to get the big picture. So what is the premise of this exercise? First of all, to demonstrate how to put a real earthquake acceleration on a simple structure. And I am making this as simple as possible. Then, how to interpret the results. That is difficult and important. Then, how about the mass? Is it on a continuous structure or is it in a discrete lump? Then, this is not advised. Don't do this at home. Or do it with a trained professional if you are doing it at home. But displacement versus time at the base. I'll explain why I did this. Then a well-known earthquake comparing to International Building Code response spectrum. And then finally, confidence, that you can do this. I think you should do this example every step of this example, and if you don't understand something, dig into it to unpack and keep it simple. So what is the simplest structure? A cantilever. So it's fixed at the base and we will subject it to an earthquake in the X direction here, laterally or horizontally. Doesn't matter what you use. I made it 10 feet long or 3 meters long. I made the cross-sectional area very large and the shear area very large so that I would have a classic 3EI over L cubed stiffness for the lateral stiffness of the cantilever. If you don't understand that, go back to your structural mechanics courses, okay? So I made it steel. I used a reasonable moment of inertia. Here it is in imperial units. Here it is in metric units. That's not important right now. And then I'm using the historic El Centro earthquake that really did happen in El Centro, California. It was a very long earthquake, 30-something seconds, 32 seconds, and very well documented. Now I'm going to do this two ways. I will do it without lumping the mass, just using the mass of the element itself. And that is your preferred method, I think, because when you draw your house, your 50 by 50 glass house, just keep it simple and understand how does that glass house respond to a seismic event. But then I also lumped 1/2 of the mass at the tip of the cantilever, figuring that SAP probably does that. SAP2000 probably puts half of the mass on one node and half of the mass on the other. And this is literally just one element long. I didn't mesh this or anything, one element. So what is the weight of the beam? Well, the weight of the beam is easy to find because what you could just do is create a beam and then display the reactions for dead load. So on your analysis, analyze, we'll run the dead load. We'll run the modal. I'll talk a little bit about modal. Let's run all of these, my response spectra and my, that one, don't run that here. Okay, so notice I am using direct integration time histories for the dynamic loading here. So let's run these here. Okay, run now. And the first one is static. I just want to see what the dead load is of the beam here, of that single element. So I could just display, so show forces on the joint, and I'm going to do it for dead. And there it is, and you could right click on it, and all I have is an axial load, X, Y, Z, or Z, 1, 2, 3, and it's 3,400 pounds. Which is 15,000 newtons, okay? So now I put the El Centro acceleration in there. And what am I looking for? I am looking for the base shear horizontally and the moment. Now, the moment should be that force, which is the base shear, multiplied by this distance, because there's nothing else happening here. So the force is easy to find from the output. So notice what I just did here. First of all, I'm clicking the envelope, not the time, because, you know, how do I know what the worst is? But here's the envelope, and I'm using it for my El Centro load case of acceleration, and I want the displacement. It'll all make sense here shortly. So there's the displaced shape as an envelope, and you'll notice it is 0.74 inches, which is about 0.02 meters. So what is the force? Well, the force should be the beam stiffness times this displacement. And what is the beam stiffness? 3EI over L cubed. So I can do that in pounds per inch or newtons per meter, it doesn't matter. And I can get the base shear, which is what it should be. And that perfectly agrees with SAP. So I could display the forces at the base for El Centro on the envelope. And here it is, 3,863. And you could right click on this and then you get the moment, M22. Put your thumb coming out of the page. M22 is your thumb. That is the bending about the y-axis. X is horizontal, Z or Z is up. Y is coming out of the page. So it's 463,574, and the force is 3,863. So 3,863 is the force. That's 17,000 newtons. It agrees perfectly with SAP. And the moment is 3EI over L squared times delta. If you don't understand that, I can help you. It's just force times length, really. And that is 463,562, which we just saw here. 463,574. It's good enough, okay? So it's perfectly agreeable there. That is for the distributed case of the load, a mass in the beam. Then I took the, I made the beam zero weight. Please make it zero weight. If you try to do the analysis on a zero weight beam, it will give you a reasonable error. It won't work. So you could lump the load, the mass, excuse me, you could lump it on the tip. And how do you do that? Very easy to do. But I don't recommend this. I don't think you really want to do this. This is the tip. Right click. There it is. You could see the location. Touch this. Assign joint masses. And you could assign it as a mass, but Ashraf is saying, hell, you could do it as a weight also. And that would be pounds in the United States or kilograms everywhere else except Rwanda and the US. Okay, so very easy to do. Remove the weight of the beam, lump half of it to the tip, and then you get the exact same answers, 0.74. Obviously, the beam stiffness doesn't change. The moment is the same before. Everything works beautifully, super easy. Now, how do you actually get the time history in here? That is not trivial here. So first of all, you want to define a load pattern always and call it something distinctive. This is a two-step process. You need a load pattern and then you need the load case, okay? So the load pattern might be something like my El Centro load pattern or something very, very distinctive. Now we need to pull in the time history of the of the earthquake. And that is something that I will give you. I will give you this ground displacement versus time versus acceleration. This acceleration is in G, gravity. 9.8 meters per second squared, or 386.4 inches per second squared. This is every 0.2 seconds. This is the earthquake. So how do you pull that in? You say define functions time history, and you will pull in here from file, add new function, and now go find that function. Go find that function. Here it is. Here it is. Go find it. Tutorials, central. Go find it. Acceleration. Boom. And doesn't look right. It's got to be time and functions, and then refresh the graph here. And kaboom, kaboom, you see it. You could bounce your mouse around here. That is what you want to do. You want time and function, or you could do values equal intervals of time, but this one happened to be time and function. Refresh the graph there, okay? So that is this time history here. It looks like this. Now notice it is about 0.3 plus or minus 0.3 gravity. So that is what you want to do. You want to, then you want the, so that's the function, the time history. Then you want the load case. You want to add a new load case and call it something distinctive, like demo, or, you know, not demo, call it like El Centro, blah, blah, blah. And here, be careful. Here, we be careful. It has to be time history. And I assumed it doesn't matter what you use for the solution, but I could not get this to work for modal. So please use direct integration. I wrote to CSI. I don't know if there's a bug or I'm doing something wrong, but use direct integration. This worked perfectly. And this is what we do in school anyway. We use Runge-Kutta or Newmark method or whatever. Now here, the load pattern, please hit acceleration. Please hit acceleration. It's super important. And this is the direction. What direction do you want? Global X is 1. Global Z is 3. So we want X. And now this function that you just described or defined under the function. And then the scale factor, super important, 386.4. 386.4 if you're in imperial units, okay? Before you hit OK, check your time steps. I need 1600 time steps at 0.02 because I have 32 seconds of the earthquake. So, and the earthquake was in 0.02 seconds. So I made it 1600 at 0.02, and then you have that. That seems to work just fine. Run it, analyze, run analysis. I think we already did that, but let me just run it right now again. And then the output. How do I get the output? The output is super easy. You can show the displacement, as I said, as an envelope, or and hold your mouse here, and that's my 0.47, or you could show the bending moment as an envelope, not as a time step, but as an envelope. Oh, okay. So then things got crazy here, and I don't recommend that you do this, but I'll walk you through it. So what I did was I used the help of my colleague, Professor Peter Larsen, Mange Tak, he's from Denmark. And what he did was he helped, he actually did this, I didn't do it. He integrated this twice to get the displacement. There's a little bit of a shift that has to happen so that you don't have an initial displacement. And what I have is the displacement of the El Centro earthquake versus time. Notice this is about 8 inches or 0.2 meters, very large displacements. And I was curious to see what would happen if I applied the time history to the base of the building as a displacement versus time. Ladies and gentlemen, don't do this at home. It's too dangerous. It's very weird. There's a weird thing about it. It works. I did this crazy thing here. I did, and I don't really know if this really works or not. Assign joint load displacements, and here you have to put in the pattern that you want, and I have the ground displacement pattern, and here you have to put in 1 inch, and this drove me nuts. I don't know why you have to put in 1 inch. If you put in a 0, it just stays at 0. So you put in a 1 inch. Now what is that displacement pattern? It's the exact same thing. It's under functions, time history, and it was L central displacement versus time. You could see it right here. I pulled it in the exact same way as time and function values, and there it is. You could see it. There's the 8. You could see 8 inches or 0.2 meters right there. That's the worst displacement, okay? So once I did that, it worked great. I don't recommend that because, you know, it's kind of crazy. But I wanted to see, well, what would happen if I applied this? And it worked perfectly. I got the exact same answers. Obviously, the tip deflection is wildly different. Wildly different. So here I'm going to do it again. It's a little bit more than 8 inches on an envelope here. So I'll show you. I will display for ground displacement versus time envelope. And it's something like 8 inches, 8.4 inches. But notice the base is moving here. So this is kind of fun. Let me just show you the video because the video I think is pretty fun. So this is due to the ground displacement. And you could see, I magnified it a little bit. You could change it to any scale, but here the base is moving. You could see the base moving, right? And that goes on towards until the end of the video, where now I'm at 16 seconds. It's a 32-second earthquake. The building is still shaking. The base is clearly moving. I magnified this to show you the movement. Now this is this El Centro time history as acceleration, but it does not move the base. This is the thing that students don't understand. It's a pseudo force. Go back to your theory. It's M times U ground double dot over time applied as a load. And that's exactly what a SAP is doing, but the M is tricky. It could be a lump M at the tip, or it could be the distributed M. I recommend the distributed M. So that is great news that it all works out perfectly. It's the exact same thing as I mean, literally the exact same thing. I got the base shear to be exactly what it was for the earthquakes. Obviously, the tip deflections are wildly different, but the base shears are literally exactly the same as before. So that's terrific news because it proves that everything's working the way you want it to work. So then I thought, well, what about the easiest possible thing, which is the IBC response spectrum? So what I did was I said, well, let's go to El Centro, California. I typed in the zip code, and I assumed a soil class D, and you could see the response spectra here. So let me just show you, find load cases, the response spectra. And what we're looking at here is it's a response spectra load case You can use different combinations. This is square root of the sum of the squares. I don't think that matters at all versus a quadratic combination. But please use the acceleration as U1 for the response spectrum that you defined, the function. And again, please put the scale factor in here. This one does use the modes. There's no direct integration here. So you want to run the modal analysis. So please do run the modal analysis before, well, at the same time as running the response spectra. Now, how do you get the response spectra? It's just the same way as the time history. Define functions, and instead of time history, just use response spectra. And there's a whole bunch to show up. I grabbed IBC, International Building Code, but you can use Eurocode or whatever. And you could change the soil class here. Let me just show you how I did it here. So define functions, response spectra. And you could see there's a whole bunch here. There's, I saw Eurocode in here, 2004, but let's use IBC 2012, add new function, and then here you could put in your zip code, by zip code, and El Centro happens to be, I forgot what the zip code is at El Centro, but you could do it for San Luis Obispo, whatever. And then you could change the soil profile. You change the soil profile. So that's how you do that. And then you save that. But notice this is acceleration. G's. And it's, you could see it's pretty high here. But what happens is the answers are much less severe than the historic earthquake itself. Where, remember, we had about 0.7 inches of displacement for the historic earthquake, or about 0.2 meters. Here we have half of that, roughly. Roughly half. And then all of the forces and moments are roughly half itself. So it's super fun, super instructive to do all this. I hope you loved this video.